So we have been discussing this frequency response of op amps. And what we had discussed in the last class is that if you assume that there is a single pole system, which means there is only one RC time constant, and that RC time constant in this case is coming from the output of the op amp. There is output impedance or output resistance of the op amp, and you always have a parasitic capacitance that results in this overall first order single RC pole. And because of that, the transfer function of the gain would look something like this. Even if you're just considering the open loop gain of the op amp. So this is the open loop gain of the op amp. E0 signifies the DC gain or the zero frequency gain of the op amp. But that zero frequency gain reduces as you increase the frequency, and overall the transfer function looks like this. Now, if you put this value of A, that is the open loop gain of the op amp, in the equations that you have already learned before. So this is nothing new. So the previous equation that you had learned was how the loop gain of the op amp looks like, and the loop gain of the op amp T is A times beta. Now, instead of T being a constant value, now T will also be a function of frequency because A is a function of frequency. So in a closed loop scenario, you'll have the same formula once again. Your closed loop gain will be A infinity divided by 1 plus 1 over the loop gain, and the loop gain will be a function of frequency. A infinity being an ideal op amp, in that case, you do not need to consider it as a function of frequency. Now, if you just write that down, that A infinity divided by 1 plus 1 over tau or 1 over T, and T you can represent as T naught divided by 1 plus J times F over F1, where F1 is the open loop pole frequency in the loop gain. It's the open loop pole frequency in T or the open loop pole frequency in A or the original op amp. Once you put that op amp in a closed loop scenario, that is, you have a feedback along with the op amp. So that's the difference between open loop and closed loop. Open loop is just this, that you have the op amp and that's it. This is open loop. What does closed loop mean? That you have some kind of a loop around it. That okay, maybe you have an op amp configuration that looks like this, that you probably have let's just say you have connected the input to the positive terminal, and you have some kind of a feedback network going from the input to the output. So let's just do the opposite, because I wanted to show you the inverting op amp configuration. So this is the inverting op amp configuration where you have applied the input to the negative terminal. Your positive terminal is an AC ground, and you have a feedback going on. So this is the closed loop scenario, and this is the open loop. So I guess the open loop versus closed loop is very clear at this point. And in open loop, even in the open loop scenario, you have a pole because of the output resistance and the output parasitic capacitance of the op amp. And that's why that open loop pole, which is at, let's say, for example, F1, and the open loop gain is A naught. Right? That's how the frequency response of the op amp looks like when your x-axis is frequency and y-axis is the magnitude of your gain. That's how the open loop gain of the op amp will look like. The closed loop gain of the loop gain, if you are considering just the loop gain, which is T, that is A times beta. Now you already know that A looks like this. You just multiply it with beta. That will give you your T. So your T or the overall loop gain will look exactly the same. That it will have a pole at frequency F1. This is your frequency. This is your magnitude of T. And what is this magnitude? The highest magnitude that T can have. That we are calling T naught, which is nothing but A naught multiplied with beta. Okay, so that's it. That's all it means by the open loop and closed loop scenarios. Question?
So, if I'm understanding correctly, the open loop scenario
is
just the op amp below.
Yeah,
like
that's
not in a circuit at all.
It can be in a circuit. You can still connect your input. Let's say you connect a 1 microvolt input in an ideal op amp, and you have a gain of let's say 1000. So you get a 1 millivolt output. So it can still be a circuit, but there is no feedback loop. The meaning of loop is that you have a feedback, right? That's the meaning of having a loop, that you have something coming from your output to input, and only then you can create a loop. So whenever you encounter this term closed loop, it means that there is a feedback. Whenever you encounter the term open loop, it means that there is no feedback. The circuit might still be operational, but there is no feedback.
At that point, it just be the difference. The
voltage difference at the input multiplied with the gain, that will be your output. That's the open loop operation. And the open loop operation will also have a frequency response like this. The closed loop operation, the frequency response of T will look something like this, what I have drawn here. So that's just T. That's just the loop gain. And the loop gain has a frequency response which looks like T naught over 1 plus J times F over F1. All right. Now, if you put that value of T in the closed loop gain equation, the closed loop overall gain. So, for example, you know that for this circuit, if this is R2 and this is R1, if this op-amp is ideal, your gain will be minus R2 over R1 at DC, at zero frequency, right? Minus R2 over R1 at very small frequencies or DC frequencies. What would be this gain as a function of frequency? That's not this curve, and that's also not this curve. You already know what would be the overall gain. So this is basically A infinity, right? Minus R2 over R1. It's A infinity. This is also A naught. That okay, this is the gain you have from this particular circuit when you have a DC frequency or a zero frequency. So what would be the overall gain of this circuit as a function of frequency? So that would just be A infinity divided by 1 plus 1 over T, where T is a function of frequency. Again, nothing has changed. This is something we have been learning for last 2 weeks, 3 weeks, right? Nothing has changed. Only the fact that now your T has become a function of frequency, and that looks like this. So your overall closed loop gain will be A infinity divided by 1 plus 1 over T. You write T as T naught divided by 1 plus J times F over F1. You ignore this 1 over T naught term because that is very, very small. You come up with this equation A naught divided by 1 plus J times F over T naught times F1. So this also looks very similar to the forms that we have written before. So for example, the open loop gain of the op-amp is A naught divided by 1 plus J times F over F1, where F1 is the open loop bandwidth. F1 was the open loop bandwidth. This is the open loop bandwidth. And this was your zero frequency gain. If you look into the closed loop equation now, the closed loop equation also looks very similar. That you have A infinity on the numerator. In the denominator, you have 1 plus J times F over T naught times F1. So what's the only difference? That your closed loop bandwidth has become T naught times F1. And you already know that your closed loop gain reduces by a factor of this T naught. Right? So what is your open loop gain? Open loop gain is A naught. Closed loop gain for an ideal scenario is 1 over beta. So to reach 1 over beta from A naught, what do you have to do? You have to divide everything by A naught times beta. You have to divide this open loop gain of A naught by a factor of A naught times beta, which is equal to T naught. So this is equal to T naught, right? So you have to divide A naught with T naught to get to the closed loop gain. As your closed loop gain is reducing by T naught, your open closed loop bandwidth is increasing by T naught. The gain bandwidth product remains constant. So in the open loop scenario, this is what you have. So if I just draw it on the side like that this was your open loop gain, right? For the op-amp. And if this was your bandwidth, let's say F1, the gain bandwidth product is A naught times F1, right? Gain multiplied with bandwidth. And the gain bandwidth product can also be defined as this point where your y-axis, which was gain, and x-axis is frequency. So at this particular frequency, your modulus of gain, or the absolute value of the gain, becomes 1. This point. So what is that frequency when your gain becomes 1? That's also termed as the gain bandwidth product frequency. And why is that true? Because you know that in this region, in the region where the gain drops, this drop is 20 dB per decade, minus 20 dB per decade, which means that if your frequency increases by 10 times, your gain will reduce by 10 times. So if your frequency increases by X amount, your gain will reduce by X amount. The gain bandwidth product will remain the same. Correct? So at this point, when your gain has become equal to 1, so let's say this value, and in this plot, at this point, we'll assume that the gain is 1, which in dB scale is equal to 0 dB. So if this plot is in dB scale in your y-axis, if it is in log scale or dB scale, this point is 0 dB. The y-axis value will be 0 dB, which is equal to 1. So your gain is equal to 1 at this point. What would be the frequency? Because your gain bandwidth product remains constant, the frequency will be equal to the gain bandwidth product because gain is equal to 1. So gain A0 times F1, A0 times F1, that is your gain bandwidth product. That is the gain, DC gain multiplied with the bandwidth. As your frequency increases by 10 times, the gain reduces by 10 times. The overall gain bandwidth product remains constant. If the gain becomes 1, the frequency is A0 times F1, so that the gain bandwidth product is still the same value. So that's why we say that the gain bandwidth product of the op-amp remains constant. Now, what is happening in the closed loop scenario? This is again just the open loop plot that I have drawn. What is happening in the closed loop scenario? In the closed loop scenario, you already know, and I'll probably not need to repeat that your gain reduces by T0 amount. So if I draw it in a different color, so your gain reduction is by an amount T0. Why am I saying that? Because you already know that your closed loop gain will be very close to 1 over beta if your op-amp is ideal. And to reach to that point of having gain equal to 1 over beta from the original gain of A0, you have to divide the gain by A0 times beta, which is equal to T0. So your gain reduces by a factor of T0. What would happen to the bandwidth? The bandwidth will increase by a factor of T0. Right? That's exactly what you're seeing from the equations as well. That you just write down the equation. Only thing is that you have to do this small simplification over here. That you ignore this 1 over T0 term. That comes out to be exactly in the form that your gain, your overall bandwidth in the closed loop scenario is T0 times F1. So your gain reduces by T0 times, your frequency increases by T0 times. That's what will happen in the closed loop scenario. Question? It's this. Right? So your frequency increases by 10 times, your gain reduces by 10 times. That's it. And why it, from a mathematical point of view, why it happens, that's something I explained in the previous class, last lecture. All right, yeah. How do you find the pole frequency? So you're asking that what is my pole frequency for an op-amp? That's a great question. And again, as I explained in the previous lecture, that how does this pole, why do we say that there is a pole? That pole comes from the output resistance and the output capacitance of the op-amp. Or maybe it could be the input capacitance of the next stage as well, as you are connecting multiple stages. So this RC, and again, like remember the first part of the discussion in the previous lecture, that this RC will be a low pass pole, will result in a low pass pole, and that's why you are saying that the op-amp has a pole, and that pole is at F1, which is nothing but, so if you convert this F1 into omega 1, that is just omega 1 is 2 pi times F1, right? Omega 1 is the angular frequency, that is 2 pi times F1, that would be 1 upon RC, where this is the R and this is the C. All right. So if we just work out an equation, an example, I think this will be much clearer. So for example, let's take the example that we have done in the class multiple times before. That okay, you have this, and it's the same circuit that I have drawn to represent a closed loop scenario. That your positive input is an AC ground, and at the negative input, you're connecting this VS, that's your source. You have this R2 and R1. So what would be your A infinity? Your A infinity will be minus R2 over R1. Okay. It is also given that A naught is 10 to the power 5. So this op amp has in the open loop scenario, this op amp has a gain of 10 to the power 5. That is 10,000 or 100,000 in fact. So that's the open loop gain of the op amp. The open loop bandwidth of the op amp is 200 Hertz. Open loop gain is 100,000. Open loop bandwidth is 200 Hertz. So what is the gain bandwidth product? That is A naught times F1, which is equal to 20 megahertz. So I'm just multiplying 10 to the power 5 with 200. I get this 20 megahertz number. The Rin you can again calculate, that would be infinity. The R naught you can again calculate, that will be 0 in this case. Now you can analyze the gain and frequency response for the closed loop case. You can find out what is beta. In this case, again, I'll not go through the entire equation, but what you see here is that you start from the output of the dependent voltage source. You see what are the voltage divisions that you have in the feedback path, and that determines your beta. So in this case, what do you have from the output of the op amp? From the output of the op amp, because this is an ideal op amp, your RO is 0, so you do not see any output resistance of this. Even though, okay, now this is a tricky part. So coming back to your question, that we are saying that F1 is 200 Hertz, which means that there is a pole, but we are saying that RO is 0 in this case. So of course there is a disconnect, but we are creating that disconnect just to make the problem simpler. The F1 or the pole actually arises because you had an output resistance and an output capacitance. But to make the problem simpler over here, we are just saying that, okay, we'll still assume that there is no output resistance. This is an ideal op amp with a pole magically coming from somewhere. But it does not come out magically. It is because it's a non-ideal op amp, but we don't want to make the problem so complex that it's much more difficult at this stage. We don't want to make that, right? So that's why we are saying that let's assume that the op amp is ideal, but it has a pole. But in reality, the pole will come because the op amp is non-ideal. All right. So you can find out what would be the voltage division. You first encounter the 9 kilo ohm R2, and then you encounter the 1 kilo ohm R1. The voltage that you'll see at the input side is developed, is basically the voltage that you'll see at this point, right? That's the voltage that is fed back between these 2 points. So that's the voltage across R1. So your beta factor is 1 upon 10. Okay. So what would be your T naught? T naught is beta times A naught, because A naught was 10 to the power 5. Beta times A naught is 10 to the power 4. So T naught is 10 to the power 4. Your closed loop gain will be reduced by a factor of 10 to the power 4. And your closed loop bandwidth will increase by a factor of 10 to the power 4. So if your open loop bandwidth was 200 Hertz, so this was just 200, multiply that by 10 to the power 4. That is, I'll just multiply it with 10 and say that the rest of it is kilohertz. Because 10 kilohertz is 10 to the power 4 Hertz. So you have 2000 kilohertz or 2 megahertz. So 2 megahertz will be your closed loop bandwidth. When you have put this in the feedback loop. So that would be from 200 Hertz, which was the open loop bandwidth, your closed loop bandwidth increases to 2 megahertz. But your closed loop gain reduces to 1 over beta, which will be equal to 10. All right, so that's what we are doing in the calculation. That T naught is 10 to the power 4. That's beta times A naught. The closed loop frequency will be T naught times F1 or beta times A naught times F1. That is 2 megahertz. Right? A infinity is minus R2 over R1. That's minus 9. The closed loop gain is A infinity divided by 1 plus 1 over T naught, that is almost equal to minus 8.999. So that's still very close to this minus 9 number. But the closed loop bandwidth, that has increased to 2 megahertz. So this is one way that, for example, you let's say you start with this op amp, which has a bandwidth of only 200 hertz. But let's say you're doing an audio application, which requires, let's say, 20 kilohertz, right? So how do you know that this op amp will still work, or how are you convinced that this op amp will still work for audio frequencies? Is only if you put it in a feedback loop like this, reduce its gain, because for audio application you may not need 10 to the power 5 gain. So you reduce its gain, increase its bandwidth, so that you can apply it to your particular application. Only thing that you need to make sure that the gain bandwidth product is large. So in this case, the gain bandwidth product was 20 megahertz, which means up to 20 megahertz, you expect that your gain will be more than 1. So this point, the point where it crosses the frequency axis over here, that is 20 megahertz. So anything below 20 megahertz, if your frequency is below 20 megahertz, you will expect a gain of more than 1. That's all you care about at this point, because you can always have a feedback loop and have a gain which is more than 1 and the bandwidth that meets your required bandwidth. Okay. Example 2, again, very similar. In fact, simpler than the previous one. Yes, question. Yeah. No. So the closed loop. So again, remember the two plots that I drew. Maybe I'll draw it over here once again. This is how your open loop gain looks like. Right? This is A naught. This is F1, or let's just call it F open loop, and let's also call it A open loop. Just to be very clear about the terminologies, this is gain open loop, this is frequency open loop, or the bandwidth of open loop. What is this point? This is the gain bandwidth product. Right? So this point is A naught or AOL times FOL. Gain multiplied by frequency. And why it is true that at this point your gain is equal to 1. So this is not gain equal to 0. Gain equal to 0 will be further below. So let's say at this point the value of the y-axis is equal to 1. Okay. So this is the point where your gain bandwidth product, or this is the frequency at which your gain becomes 1. And because what is the characteristic of this portion of the curve? If the frequency increases by 10 times, the gain will reduce by 10 times. So gain multiplied with bandwidth will always remain the same anywhere on this curve. If the gain reduces by X amount, the bandwidth will increase by X amount. Now, what are you doing when you are putting the open loop op amp into a closed loop configuration? Through feedback, you are sort of reducing the gain. Right? In this case, the gain was A naught or AOL, which is very high. In this case, the gain is minus R2 over R1. And if you calculate the beta factor is basically very close to this R1 over R2. In fact, the beta factor would be R1 divided by R1 plus R2, but you'll see that it will be very close to that. So the gain in this case is minus R2 over R1, which means that, and this ratio of R2 and R1 could be in the range of, let's say, 10 or 20. On the other hand, the AOL is probably 100,000. It's very, very high. So the open loop gain is 100,000. The closed loop gain is somewhere over here. You have reduced this by an amount of T naught. Okay, what is T naught? T naught is A naught multiplied with beta. And because you have reduced it by amount of T naught, this has become almost equal to 1 upon beta. So your gain is 1 upon beta. What is your bandwidth? Bandwidth is here right now. Till this point, you do not see any reduction in the gain. You'll start seeing reduction in the gain at this point, which is F closed loop. And this is A closed loop. What would be gain closed loop multiplied with bandwidth closed loop? That will be exactly equal to gain open loop multiplied with bandwidth open loop. Whether you're having it in open loop or closed loop does not matter. The gain bandwidth product will still remain the same. Which
So basically, like having an op-amp with a feedback, operate.
increased bandwidth. Yes. Gain reduces, bandwidth increases. If you go back to feedback theories, I think it's also covered in circuits 2 lectures that it explains from equations that why your gain reduces and why your bandwidth increases when you have the negative feedback. More questions? In this case, yes. Yes. Because if you want a fixed gain across any frequencies, let's say he was working on audio amplifier, and the op-amp that we just looked at has a bandwidth of only 200 Hz. So you cannot use it for audio applications unless you put it in feedback, reduce its gain, increase its bandwidth so that the closed loop is more than 20 kilo. So this is one way that you can play around with the gain and bandwidth of the op-amp and use it for different applications. So you can use the same op-amp for different applications, needing different amount of gain and different amount of bandwidth. Okay, is that part clear? Perfect. So if you look into another example over here, so here the beta factor, the feedback factor is equal to 1 because you have connected the op-amp in the unity gain configuration. You go back to the op-amp configurations that we have learned. This is a unity gain configuration or a voltage follower configuration that you are applying your VS voltage at the positive terminal. Your output will follow whatever input you are providing. Because your gain, in this case, what is the, if you did had two resistors, R1 and R2 in the non-inverting configuration. So this is the non-inverting configuration. Only difference is that we learned that in the non-inverting configuration, there is a resistance over here, and then there is a resistance over there. We do not have those two resistances in this case. So if this was R2, and if this was R1, we have already solved the KCL equation, the nodal equations, to find out that the gain in the non-inverting configuration is 1 plus R2 over R1. Okay. In this case, what is your R1? Because the R1 was not present at all, it was open circuit. R1 is infinite. Because R2 was not present at all, it is in series and it's not present, which means R2 is 0. So R2 is 0, R1 is infinite. What is the gain? Just 1. Okay. So that's the gain in this case, and that's why it's called a unity gain configuration or a voltage follower configuration. In this case, what would you expect? Let's say you have the same number. Say A0 is 100,000. The open loop bandwidth is 200 Hz. That means the gain bandwidth product is still 20 megahertz. In Rin is infinity, Rout is 0. This is a voltage follower configuration. So your beta is equal to 1. Your A infinity is also equal to 1. Your closed loop bandwidth is equal to T0 times F1, which is also equal to A0 times F1, which is also equal to 20 megahertz. So what we are saying here is that because this is in a voltage follower configuration or unity gain configuration, your beta factor is exactly equal to 1. So in this case, your closed loop gain is equal to 1. And what would be your closed loop bandwidth? Because gain is equal to 1, what would be the bandwidth? Bandwidth will be equal to the gain bandwidth what you had earlier. The gain bandwidth does not change. This is the open loop gain bandwidth product. Open loop gain, which is 100,000, multiplied with open loop bandwidth, which is 200 Hz. What is the open loop gain bandwidth product? Product of those two, 10 to the power 5 multiplied with 200, 10 to the power 5 multiplied with 200 gives you 20 megahertz. Now in the closed loop scenario, we are saying that our gain has become exactly equal to 1. So what would be our bandwidth? Our bandwidth will be, yes. Sorry, I didn't get it. 0 to the 20 megahertz. Or 1 multiplied with 20 megahertz, yes. Yeah. So, yes. So, bandwidth will be exactly equal to 20 megahertz. Keep in mind, again, this plot. gain open loop, bandwidth of open loop. And what is this intersection point? This intersection point is where your gain becomes equal to 1. So your y-axis value is equal to 1 here. And this will be called the gain bandwidth product, or the multiplication of A open loop and F open loop. In the case of the unity gain feedback, we are saying the gain becomes 1. So from A open loop, you are reducing all the way to 1. So you are reducing to exactly this line. So what is my bandwidth along this line? The bandwidth is the full gain bandwidth product. So bandwidth is this point, right? So your bandwidth, the closed loop bandwidth, in this case will be equal to 20 megahertz. So if you want the highest bandwidth out of your amplifier, you can put it in the unity gain configuration. In that case, your gain will be 1, you will not get any additional gain, but your bandwidth will be maximized. Again, similarly, a very similar problem, right? Just look into this. I'll not go over the entire problem. It says about the same things that you just, so this is example 1. Assuming the op-amp has input impedance of 1 kilo ohm, output impedance of 1 kilo ohm, and A0 of 10 to the power 5, F1 of 200 hertz. So only thing that has changed is that now we are saying that we'll assume that Rin is 1 kilo ohm and Ro is 1 kilo ohm. So what would change? Your factor beta will change. So just go over this set of equations and you'll see how that beta factor is changing in this case. And because of that, your T0 will change, right? The value of T0 will change, and the final gain that we'll have will be different as compared to example number 1. All right. So this is again, it's just an exercise that you can go over. If this is much more involved, and we'll solve these kind of problems when we look into MOSFET-based amplifiers. But try to solve this problem. We can discuss more about this in the office hours. So this is just an exercise, ungraded exercise. If you're interested in solving more intricate, more detailed problems, just try to solve and try to see if you can solve this kind of a problem. And the steps are already mentioned. So if you just follow the steps, I think it will be easier for you to solve this kind of exercises. Okay. So this was just whatever we have learned till now. This is the takeaway for your op-amps. We have looked into non-inverting amplifiers, inverting amplifiers, current to voltage converter, current amplifiers. We have looked into the loop gain theory. We have looked into how to find out the first order low pass pole, how to find out the closed loop gain and the closed loop bandwidth. And as the next steps, we'll also discuss a little bit about differential amplifiers and AC coupling. So once we discuss those, I think our topics related to op-amps will be finished. And in the next lecture, we can start with diodes. But for the next 15 to 20 minutes, I wanted to discuss a little bit about differential amplifiers. Okay. So what are differential signals? Differential signals, if you think about, there are two different kinds of signaling that we learn in this course and in the labs. One is single-ended signaling, one is differential signaling. Single-ended signaling is, let's say you have a sine wave. And that's how we define a sine wave, right? So that with respect to, let's say the amplitude of it. So this will be called peak to peak. This is a peak to peak amplitude. You can also define the sine wave in terms of its peak amplitude. So the peak amplitude is half of its peak to peak amplitude. If you want to be more detailed, you can also define what is the DC value, what is the DC level of this sine wave. So in an ideal sine wave, this DC level is usually 0, but you can also define this sine wave with a positive DC level or a negative DC level. Now, as soon as you're discussing about DC levels or you're talking about DC levels, it needs to be with respect to a reference. Like, what is the reference in this case? So you always, in your electronic circuits, you always first establish a ground connection. Unless there is a ground connection or there is a reference connection, most of your circuits will have no meaning and it will not work in most cases. So for now, it will suffice to sort of take this as a rule of thumb that all your circuits needs to have a common reference, which in most cases is a ground. So whenever you are saying that this sine wave has a DC value, which is, let's say, 1 volt, with respect to what? With respect to what are you defining this as 1 volt? With respect to the ground, right? So there is always a definition of 0 volt. And with respect to that 0 volt definition, you're saying that the DC level of the sine wave is at 1 volt. So as soon as you have two signals, even if one of them is, let's say, ground, you're talking about difference of two signals, right? So even when you talk about, let's say, a single sine wave, which in this case will be called a single-ended signaling. So this is a single-ended signaling that you're talking about only one signal. But even that one signal is with respect to something, right? And in this case, it is with respect to the ground, whatever reference you have established in the overall circuit. So if you say I'm applying 5 volt, 5 volt with respect to what? 5 volt with respect to 100 volts or 0 volts or minus 100 volts. You need to specify that. So 5 volt with respect to 0 volt. If your ground is 0 volt, if your reference is 0 volt, then applying a 5 volt makes sense. If your reference is 100 volts, applying a 5 volt will not lead you to anything. Yeah. So that's what the concept of difference of signals comes in. That you always have to think about with the difference of two signals. Whenever we talk about single-ended signaling, we take the difference with respect to the ground or with respect to the reference that we have established. So for any circuit, let's say I'm just drawing rectangles over here to represent circuit components, but it could be resistors, capacitors, other things as well. But let's say I'm just drawing rectangles right now, but you have to define a reference point, and let's say you define that reference point to be a ground. So with respect to this reference point, you will eventually find out all the voltages and currents at other points or other terminals. Whenever you're doing that with respect to a reference voltage, it's called a single-ended signal. That with respect to the reference, the single-ended value at this point or this point or this point, I can define that I can find out all the different voltages and currents at every terminal. What is differential signaling then? Differential signaling is not only difference of two signals. The signals have to be defined in a particular way. If one of the signals looks like a sine wave like this, that you have a positive cycle first and a negative cycle, the other signal should look exactly the opposite. That you have the negative cycle first and then the positive cycle. So that's how differential signals are defined. That it's not only enough to define a difference of two signals, the two signals also need to be defined in a particular way. So even in your single-ended scenario was a difference of two signals. It was a difference of your original signal and the ground level. So that was also a difference. It was not that single-ended signaling was fully functional by itself. You still needed to establish a reference ground. In case of differential signaling, it's two signals which are opposite to each other at every point. So if you have let's say a sine wave on the positive line, the negative line should also have a sine wave which has exactly the opposite phase relation with respect to the positive line. That's how differential signals are defined. What is the differential mode voltage value? So VDM is called the differential mode voltage. The differential mode voltage is if you define this voltage as V1 and this voltage as V2. So if those two are your voltages, V1 minus V2 will give you the differential mode voltage. What is defined as common mode voltage is half of V1 plus V2. So if these two are your sine waves, your average is sort of in the middle, right? That's your common mode. That's a common mode of the differential signals, which is half of V1 plus V2. Now, look at this scenario that when you have this positive sine wave or the positive half cycle of the sine wave first and then the negative half cycle. And on the other line, on V2 line, you have the negative half cycle first and then the positive half cycle. What would be the difference? What would be the differential mode signal? It will just be the double of each of those signals, right? So V1 minus V2 would look something like this. That the amplitude, the voltage amplitude in both the positive cycle and the negative cycle will become double. Right? Because if this is 1 millivolt, or let's just say this is 1 volt, and this is minus 1 volt, what is 1 volt or minus 1 volt subtracted from 1 volt? That will be 2 volts, right? So this point's voltage will be 2 volts. And this point's voltage will be minus 2 volts. So the differential mode voltage will be double of each of the single-ended voltages in this case. What would be the common mode voltage here? That would be the DC point of these two voltages. Let's say both of these DC points are defined at 0. So this is 0, this is 0. So the common mode voltage will also be 0. On the other hand, let's just assume for a second that your V1 looked like a sine wave and your V2 looked like a DC signal. This is not defined as differential signaling. Why? Because again, if you find out the VDM will look like a sine wave because that's the difference of these two signals. How would VCM looks like? That will be half of V1 plus V2. So common mode would look like a smaller, a sine wave which has a lower amplitude. So even the common mode will become a sine wave if you define your differential signals in a wrong way. So this is the wrong way of defining differential signals. Differential signals are not just the difference of two signals. Those two signals have to have opposite phase relations. So they have to be equal in amplitudes, but opposite in phases. That's how you define differential signals. Now you can find out individual V1 and V2 as a function of VCM and VDM. V1 is basically VCM plus VDM over 2, and V2 is VCM minus VDM over 2. That you can solve just from these two equations on the left-hand side. Questions?
Like practically speaking, why would you use
Why would you use differential signals over single-ended signal? Great question. The main reason, but that's what I was coming to next, is that in most of your circuits, let's say you're building a circuit on a breadboard, there would always be noise, there would always be interference. So let's say you are designing a circuit in the range of 100 megahertz, and you know that the FM frequency is between 88 to 108 megahertz. That's why you have your FM radio. So if you're designing your circuit on the breadboard or on a PCB at 100 megahertz, and you always have interference from FM, whenever you're trying to amplify your original signal, it's also trying to amplify the FM signal that is present in the environment. Right? So that is an interference, and that is hurting your implementation of the circuit, implementation of the amplifier. But imagine the scenario where you define your amplifier to be a differential amplifier, and you define your signals, input signals, to be differential in nature. So what you are amplifying is just the difference of those two signals, V1 minus V2. If you think about the FM wave, which is an interference to your entire circuit, the FM wave signal is present on the V1 line, it's also present on the V2 line. So if you take the subtraction of those two, the FM signal, which was an interference, goes away. Same happens with noise. Noise is present in all the terminals. And if the terminals are designed like very close to each other, the noise will somewhat be correlated in those two terminals. So that correlated noise will go away once you take a subtraction of the two inputs. So that's where the differential signaling is important, and that's why differential signaling is used most of the times whenever you're trying to find out or whenever you're trying to design a circuit which needs to be accurate and which is very sensitive to environmental variations. You will design a differential circuit instead of a single-ended circuit. And that's the primary reason, that you want to get rid of the noise, you want to get rid of the interference, which are common mode to each of the inputs.
So then, like noise is a fairly common thing.
Yeah.
Why would you ever use single-ended over?
Again, a great question. So single-ended differential takes double the amount of hardware. Yeah, and it also takes more amount of power consumption. So if you want to build a smaller system with lower power consumption, single-ended sometimes works if your signal levels are much higher than noise levels. So noise would be, let's say, microvolts to a few millivolts. If you know that your signal is 100 millivolts, do you ever care about noise? No, right? So you know that your signal is high enough so that you don't need to think about noise at all. Then you will use just single-ended signaling with lower power consumption, lower amount of hardware. But whenever you're trying to design something that is very sensitive, that, okay, I'm trying to amplify 100 microvolt signal, right? So that is very sensitive to environmental noise. And then you need to go with differential. All right. So I don't think that there's anything more to be told at this point with the differential signaling. It's just that keep this in mind, that this is how differential signals are defined. We'll come back to this concept when we actually discuss what is there inside a differential amplifier. So from next class onwards, we'll start discussing diodes. In Wednesday's lecture, we'll be going over a few different problems. We'll try to solve multiple problems to be prepared for Friday's exam. So next Friday, we'll have exam 1. We'll have it here in the classroom. I'll provide more details in the Canvas home page. Yeah, it will be during class hours. Morning.
Okay,